We're at the point now where we have our final invited talk, and I'm delighted that Katia Sycara is giving this, and her title sounds perfect: Intelligent Disobedience in Human Agent Interactions. I'm not sure if everyone's familiar with Katia's long history of work, but she has made many contributions at AAMAS in terms of multi-agent systems. My gosh, I first came across Katia's work in my core community of case-based reasoning, where she made many contributions earlier on. And I couldn't begin to list the number of times I've caught her invited talks and otherwise impactful presentations on a variety of topics in AI. And I'm really looking forward to what she has to say here. So Katia, thanks very much for joining us.
Thank you. I'm just going to share my screen. Can you hear me?
I can hear you.
Okay, great. And you can see the screen.
I can see the screen.
And the screen is the screen of not my emails, but
there we go.
the talk.
Right? You're right. I see the presentation mode just like you'd like to set it up.
Okay, so it's a big screen with a presentation mode.
Yes.
Okay, great. So thank you for the invitation to this very interesting workshop. And so I want to talk about intelligent disobedience and present some work that we've done with respect to this and see my take on the intelligent disobedience and rebellious agents. So let's see where we are. Yeah, this band is so intelligent disobedience. So the agent, I'm sure you've all discussed it during the talks and during the workshop, but just to refresh myself, it's a handler's command. The agent disobeys a handler's command due to a more nuanced understanding of the situation and handler's intention. Of course, this is mostly having to do with specifically to safety concerns and prevent immediate harm to the human or to the robot, or again, being safety conscious, even though immediate harm may not be present. And Ruth, in her 2021 paper, gives the example of a wheelchair, where if it is in a crowded thing, it can try to really slow down. I mean, it's not that there is any particular immediate threat. So on the other hand, the rebel robots, they refuse the assigned goals and plans and oppose behavior of other agents. And this is more general because there are many additional situations, not just safety concerns or another person's intent, but the robot disobeys unintentionally, disobeys imperfect instructions, disobeys due to egoistic. So for example, fulfilling its own goals, having its own goals, and doesn't want to be bothered with others, or altruistic, that do not want to harm others. So given a soldier some particular command, for example, a soldier may refuse to hurt somebody. So on the other hand, you know, one could say that these two notions obviously overlap, and in particular, in intelligent disobedience, the human has, one could say, has given imperfect instructions in that the human has not thought deeply about the situation. So this would be in the immediate harm, for example, to the human, right? The dog, they see an eye dog, disobeys the command of the handler, and when it sees, for example, a bus coming, and the handler may not see that. Okay, so what we are interested here, that I'm going to present, is advice giving as and refusing advice. So advice giving and, of course, refusing the advice is basically imperfect instructions or things that have not been planned and are not correct. So the person, the commander or the teacher doesn't give correct advice. So intelligent disobedience in a human-robot interaction is we examine this human or agent, could be a teacher, and advising another agent as a student. And of course, the student could decide to disobey, and we'll see how and why. Now, on the other hand, one could also think about the other thing. We're studying now disobedience and how it comes about, but on the other hand, one could think about preventing intelligent disobedience. So if somebody is rebellious or it does not obey for whatever reason, now the agent that it could try to convince that person or agent not to disobey. So that's another issue that we are going to talk about. And so in terms of our framework, it's in the overall work area of teacher-student framework, where one looks at things like what is the goal of the advising agent, what we would like with intelligence reading, what we want, why do we want, what is our approach, and how do we implement that. And so this idea is that advising in that framework is seen as knowledge transfer from presumably an optimal agent, a teacher, that imparts during learning some advice to the student. And so the student's trying to learn. And so the idea is that by giving this incremental advice or this advice, however it is given, the student learns and it's helping the learning process. And so, of course, it's related to reinforcement learning, but up to now, the two communities have not really been, in sync with each other or using each other. And so the student-teacher policy on action advising, so in the literature is mostly on action. And what happens is there is the world, there is the state, the teacher observes the student and also observes the state of the world. The teacher has been trained in is optimal in the particular situation, the particular scenario, and it can impart action advice to the student. The student, in most of the work, is assumed that the student will accept the advice and performs the action in the world. The state gets a state reward, and this repeats. And so this is this action advising thing, and traditionally receives this advice on the action and obeys. So the motivation is, of course, in IRL, what is the difference and what is a little bit of a difference is that the IRL assumes offline data set and recovers the reward functions. On the other hand, in teacher-student, the advice is given during the learning. And then when and how is the teacher giving the advice? And there are some questions here. Why not give the whole teacher policy to the student agent? Why give incremental? And so it may not be useful in many situations. So for example, the teacher or the student may not be an agent. So it may not understand I have these two parts that are really, they cannot really even communicate with each other. The teacher and the student may have different models. It is difficult for incremental learning if the learning one wants to actually have the student really learn little by little. And of course, if one needs to learn only the teacher's part of the teacher's policy, and we'll see that. And so the teacher may be suboptimal, and we'll see some of that. And so there are many situations for the agent's advice in our life. So this idea of the framework for humans, actually, so the idea here in Torrey and Taylor is that really the advice that is given should also take into consideration, although their work was only for agents, but the idea is that one should take into consideration human capabilities and limitations, and so they introduced a budget. So in other words, if there is continuous communication at every tick of the clock from the agent, the human is going to be overwhelmed. And so the idea is to have some kind of a budget, and the overall then amount of advice must be limited. And there are some works subsequent that adopt this concept, and we also do. And so there are now some computations, some limitations of models for the human students. Very few subsequent works that explore these details of what happens, in terms of the budget. And there are no human experiments so far And we haven't done either, but we're setting up to actually do that. And I'll say some additional things about later. And so, on the other hand, considering humans and how humans behave and how humans learn, from cognitive science, we know that explanations increase the human learning process, in particular, self-explanation. So a student tries to, when faced with a situation, tries to explain the problem, how would it come about, and tries to explain it to himself. And so the research question that we're looking at is, can we augment the teacher-student framework so that the teacher imparts action advice as well as the explanation? So is that beneficial? And so we examine to look at where students are artificial failures. And we, in future work, we want to advise humans. And so if we want to advise humans, also, of course, the giving a particular type of explanation, as we will see, in an intelligible way for the human is going to be helping. So one of the motivations of this approach that we're taking is not only to give explanation, because that would help the teacher, the human, I mean, the student learning, but also that the explanation is going to be intelligible. So these contributions then is we augment the advice with useful rationale, hopefully generate interpretable decisions. And we can also, we have looked and we will see in the results that this particular EAA can also be on top of multiple teaching algorithms. So one could have particular teaching algorithms and then have EAA explanations on top of those. And so the other thing that we are very interested in is to have teams, as we've seen, not to have just one student, one teacher. And we are starting with teachers that would be able to teach more students. For the time being, we are looking at a team with different, where the students have different roles. And so we have a teacher and student, each one according to the role. Now, it is not really as a single model, because it can be generalizable to various teams. So you can have teacher in role A and many students in role A. And so in that respect, it is different than just having a pair of only teachers and students, single teachers and students. And of course, the other thing is, of course, that depending on what the different roles do, the world is not totally, I mean, the teacher doesn't know exactly what the other role student has been doing. So there is a little bit of ambiguity there and not full information. And so here is background to reinforcement learning. This is presenting this to the choir. And we all know what an NDP is, the set of players, set of states, set of joint actions, reward function, transition function, and discount factors. And so this is just for the sake of completeness, I present that. And of course, everybody here knows that. And so the goal again is to find a policy that maximizes the total reward. And so overview of our EAA approach. So we have a teacher policy. Out of that, we have a representative policy, and we will talk about that. And then there is a policy gives the teacher's action, and the representative policy gives action plus the explanation. And this is given to the student, and the student has a policy, but also the student has memory. So that's the other thing, that the student can remember the advice and the explanation. As a matter of fact, it can remember the explanation. And so the student then does an action in the world and then gets the reward, and this repeats. So what is the procedure of our approach? The teacher computes the advice and the explanation. The student uses the advice and explanation, attempts to mimic the decision of the decision-making process of the teacher. And the student augments his own decision-making then with this information. And so how the teacher computes the advice. And so now we have a background of providing explanations, and the explanation is in the form of decision tree. And decision trees have been used to model data and solve many tasks. The graph, of course, is the V is the node set and D is the agent set. And the nodes refer to features to split. So for example, there is the root node, and then there are a set of questions, yes or no. And then at the end, the edges determine the branch to traverse. And the traverse path explains how the output is produced. So the output is the action, which is in the leaf node. And then the path is the explanations of what led to taking this action. So the input is the state or a history of states, the output is an action, the explanation of the paths. And so here, what we do is we leverage Viper, which is a particular procedure there to extract a representative decision tree policy for the teacher. And so the idea here is that there are some ideas from compression and imitation learning. And so the technique is through collection data of the given DNN policy, it extracts Viper, extract the decision tree policy that best represents it. And so the technique also guarantees convergence and stability that is being proven in that paper. And so the algorithm assumes there is a pre-trained policy, P star, that it wants to extract from. It samples trajectories under the given policy as the data set. This is the P star, samples trajectories. Next to merging, it proceeds with resample according to the loss. And after resampling, a new decision tree policy is run, and finally the best tree is selected based on cross-validation. And so in this particular way, we can use Viper to extract a DT policy. And the DT policy is highly representative because it provides advice on both actions and the explanations. And so to be more specific, given a state, the DT policy outputs the probability over possible leaf values, which we may sample to get our action advice. And each path leading to a given action represents the rationale, telling why the results make sense. And in this way, each piece of advice can be comprised of the action plus its explanation. And then you might already notice that since we can extract the representative DT policy, we technically don't need the original teacher's policy anymore. However, we still keep it because it does not perfectly represent the original policy. The DT policy does not represent the original policy. And so this is our procedure. And so we consider here how the user uses the explanation and the actions. And given that the student may receive advice on action explanations, then we want the student to use it. The student can use it in these various ways. Reusing advice is advantageous because it can lower the teacher-student communication frequency, right? The student doesn't need to ask, why are you telling me, or think about that. And the other thing is this DT can form partial knowledge of the teacher, for example, and that can be reused by the student. So it's more like a self-explanation. And then the third is that the advice might be generalized to novel states, and we will try to see that. And so the steps that to reassemble the DT into the memory is the 3 steps. First, we filter the data and keep the advice with DT path explanations. For each collected path, which is a list of nodes, we then want to update our in-memory DT Here, the U0 is the root, UD minus 1 is the leaf, and so on. Each pair of adjacent nodes has a relation of parent to child. And so second, for each path, we find the topmost node that is not in the current in memory. And this implies that the remaining nodes in the path also do not exist in the branch. This has not been seen. And so if we cannot find the topmost node that is not in P, that means no node needs to be added. So we have already seen this explanation before. Then we directly add all the children according to their inequality signs, and the collected paths all originate from the teacher's policy, and so there are no conflicts when they are assembled this way. And so now we need to reassemble the DT in memory, and so we can look at an example. We consider the state features, the teacher's policy, and the teacher's DT policy. So we assume that there are two agents here, and one is looking, and they are collaborating for something, to save victims, for example, in search and rescue. And so if the teammate is not here, then that one should enter, because that means that the room may not have been searched. So one does not want to make actions that are, to make decisions that to go into a room where somebody else is, right? Because they don't want to duplicate. So the player then needs to decide whether to enter a room, and there are two actions of entering and not entering, and contains these features. And so, for example, we start with a root. So we say, is the teammate not here? Is the room not dangerous? Then if both of them are yes, then you can enter. On the other hand, if there is the no teammate, but the room is dangerous, do not enter, and so on. And so now, so the first path can just be directly copied if the student's memory is empty. So the student can memorize entering into the room, and also if the room is not dangerous, then you can enter. And so now we have seen that the advice on action explanation are reassembled, and now we can discuss how the student chooses the action. It not only has the action choice under its own policy, but is given multiple resources for making this decision. And so first is the teacher's policy, is one of the resources that it has. And second is the DT policy of the teacher. Third is the students in memory subtree of the policy. And fourth is the student's own policy. Because what happens is in cases where it is not, there is no explanation, and none of these other sources of information can provide some advice, then the student takes its own action under its current policy, or it can engage in exploration to actually find a good solution in the situation. So this is just saying in words what I just said. And so what we test here then is Minecraft. So we do our experiments in Minecraft. Minecraft is a well-known 3D video game. It's an easy tool for realistic scenarios. And so what we have here, and we study how autonomous agents give interventions to teams in a simulated urban environment. This we're using in another project that we have, and we'll talk a little bit about that more later. But the scenario that we want is, here is the player's view and the bird's eye view of the map. And the studies show how autonomous agents give advice in an urban search and rescue mission. And so our experimental setup scenario is, here is the goal, to rescue victims. And some of the victims are beneath rubble. So what we have two roles. We have an engineer that can remove rubble, and the medic can heal victims. Both of them can navigate into the environment. And the reward is that the team of these two players is rewarded when the victims are healed. So in other words, cooperation is needed, and the engineer removes the rubble first, but the engineer, by removing rubble, doesn't get any reward. The team gets the reward when the victim is healed. And so we use comma from our policy, but as we said, the AAA is not limited to a particular algorithm. And here we have partial observability, and the belief is one hot vector encoding the presence of victims, rubble, and the teammate. And so we have two sets of experiments in a small real-world environment with 4 rooms, and also in 14 rooms transformed from the Minecraft environment, from a Minecraft map. And so in the small environment, we have 5,000 episodes, average of 100 evaluation episodes every 40. And episode maximum number of steps is 40, maximum budget is 300, and each teacher trained by Viper reaches an accuracy between 96 and 99. So this is our optimal teacher. And then in the environment, the second environment, we have 16,000 episodes, gain about 100 evaluations, and episode maximum number of steps, and so on, maximum budget 10,000. So the thing is when to give advice. So we have these experimental benchmarks, and we look at them, and these are the particular advice, types of advice that we are using as in Torrey and Taylor. So the early advisor, very early advising, is advice is given at each time step, and continuous advice is given until the time point where the budget is used up. And then the teacher doesn't give any advice anymore. So here, the alternative advising, advise with a fixed frequency over the whole period. Importance advising, so the teacher gives advice when the state importance is greater than some threshold, and the state importance is the difference between the max and mean expected reward in a state that can be achieved. And then mistake correction advising is advice when the state is important and the student is going to take an action different from the teacher's advice. So that means then the teacher would give advice to correct the action. And so here are the experiments. And what we see here is that for environment A, the EAA variants dominate the heuristic action advising, except for the importance. So both the all these variants are the heuristic early budget up. The EAA dominates both of those, and also needs fewer budget. And and so mistake correcting advising, important advising. And so what we can see is that really these lines, here you can see my cursor here, they show the budget when the budget finishes. And so we can see really that for others, when the budget finishes, they drop, their performance drops, whereas with the EAA, it is it continues. So the other set of experiments that we did is that we have for the environment B. So it is similar kind of comparison, more obvious advantages for the EAA versus the heuristic, and in all situations except for the importance advising. And we also did some benchmarks with other works in the literature that we use advice. And there are different works in the literature where they reuse advice. And so rather than we use the explanation, these are without explanation. So in this particular case, there is a save state and action of the advice into the memory, and there are different algorithms. They could change per step and decay reuse probability. and reusing the budget, having a big budget for each case. But they are conceptually similar to AA, but there are no explanations. And another one is learning to teach, which considers the teaching as an RL problem that the teacher need to learn whether to give advice or not. And the teacher also learns to allocate the budget. And there are multiple sessions. And so here in the experimental results, again, with those benchmark algorithms, and here we only show the median. Among benchmark, Q change per step performs the worst. It assumes a strict increase in Q values. Otherwise, the stored advice will be discarded. This can hardly be the case for cooperative definitions with sequential dependency. You do not want to discard advice. Decay reusing probability and reusing budget can make students finally achieve near optimal teacher, and the second pairs are only good for determining deterministic missions. And learn to teach policy can only be learned after the student converges, so the algorithm is much slower. And so these are the different, again, what I said in words there. And we have the conclusion of this part that says that explainable advice giving is advantageous because it augments the existing teacher-student framework, provides action advice plus explanation, and it improves the policy reward, convergence speed, and provides the explanations. And also what we saw is that because it converges faster, then that means that the student learns faster. And yeah, it also reduces communication frequency. Now, what we want, so this is the student teacher framework where the teacher advises the student. And so now we want to look at and say, well, let the student reason over this DT policy and accept, let the student decide to accept or reject the advice accordingly. And so we can think about that the student may not want to accept the advice when the teacher is suboptimal, for example. And so far we have assumed that the teacher is optimal in the student's environment. However, the student should reject the advice if the new either in the new environment or if the advice is suboptimal. And so having the explanation in memory is a way of actually enabling the student to do that. And so what we have here, again, we have the teacher's action, the representable policy, and the explanation. And we want the student to examine the advice quality and then decide of whether to accept or reject the advice. And so again, this is an example that we have run some experiments on. It's trained on an environment without rubble, and the student needs to remove rubble to save victims. And so this is more like, again, transfer learning type of thing, but it's different because the student in this particular situation should ignore the advice if there is a decision feature when transversing the rationale in the student's reasoning that contains rubble, okay? Because the teacher does not deal with the rubble. This is what we would like to do, right? And so in that case, the advice should be rejected. So if we look at the teacher's policy for the engineer, we say, is the room safe to enter? Is there any rubble in the room? So yes, it's safe to enter. Is there any rubble in the room? Yes. And then, okay, then in that case, call the teammate because you can start, collaborating on saving the victim. On the other hand, if is the room safe? No. Is the teammate nearby? No. Then leave the room. Is the teammate nearby? You can call the teammate because then both of you can do something. Right? And so ignore because the teacher has no expertise about rubble. So here, no matter what this leaf is saying, what this action is saying, then this should be rejected because the teacher's policy does not really mention rubble. I mean, the teacher, that the policy that the student would have. And yeah. And so on the other hand, I accept the advice if the environment has been observed and the advice is reliable. So we did some experiments where we trained the environment, the teacher in an environment where there's no rubble. And then as background knowledge for now, for simplicity, we said, okay, if the player's role is engineer, don't give advice if there is rubble in the room. And so what we did, we compared multiple versions of AAA and also pre-trained models. And what we see here is that if we have, for example, this gray area, this gray line is, and this is the reward, right, in the episodes. And the teacher always gives this advice. It transfers the whole NN, right? But because, of course, it has been trained on a different environment, it doesn't perform very well at all. If we pre-trained with a teacher's NN, again, we can see that it is really very late of starting to actually converge. And on the other hand, if we have the EAA alternatives, we can see that they are much better. Oh, and also we have this trained from scratch. So the student doesn't know anything, doesn't take advice, it just trains from scratch, does the thing itself and converges. And we let it run for a long time to make sure that they converge, so we can see the whole trajectories. And then we see the very many variants of EAA actually do much better. So that is the idea, that the student now remembers what the advice and what the explanation was, and of course the actions that have been advised. And looking at the explanation is able to make a decision of whether to reject or to accept the advice. And so the second part now that I want to talk a little bit about is preventing intelligent disobedience in HRI. And so suppose the teacher now is advising a human student, and this is our situation, the ASSIST project, where we have to advise, our agent has to advise a team of humans, which is much more challenging. And so the goal is now, how can the teacher make its advice convincing so as to minimize the disobey decisions of the student? And so, of course, we receive advice from agents in daily tasks. And what we see here, for example, for the GPS is it says here that there is an incident ahead, take the next exit. Okay. So this really tells you, if it just tells you take the next exit, and you really thought you've traveled this road, and you really say, why is it saying that? I mean, it's really bizarre. But if it says, okay, there's an incident, the road is blocked, or later on there is some accident, or there is construction or whatever, but it's not apparent to you, then of course, if the GPS says that, then the person is much more likely to obey. And so that kind of the idea here is that if the advisor has artificial social intelligence, and this is what we are trying to construct in that project, in the ASSIST project, to construct an agent that has artificial social intelligence. And in this scenario, again, is the Minecraft search and rescue. Here we have 3 players advised by the coach, and the red is the medic, the middle, the yellow is what is called a transporter, because after the victim has been healed, and now there is an evacuation step that the transporter transports the victim, and this is the engineer, and here would be the coach that advises the team. And so the players have to clear rubble, stabilize the victims, the engineer clears the rubble, the medic stabilizes the victims, and all 3, or the transporter in particular, because they have different velocities and so on, can evacuate the victim. And only the victim, when the victim is evacuated, then the whole team gains a reward. And so the coach communicates to the players, corrects mistakes, and suggests strategies. And so here is one of the things in intervention log. So our agent, so here is the Minecraft, how they go. And so the wrong victim marker. So our atlas is the name of our agent, says medic, you identified a victim, but there are different types of victims, and the medic is supposed to put whether it's the victim is of A type or B type, because they have different injuries and they need to be evacuated in other places. I mean, in various different locations. And I have another video with longer explanations that I can play. We call it interventions. And so the idea here again is explain why this advice was given. And so we all have explanations that we are now looking to actually do experiments with humans to see if we give explanation versus if we don't give explanation, what the rate of compliance to the teachers, I mean to the coach, the teacher's advice is going to be. Okay. And the coach so basically the way the thing works is that the agent looks at what the people are doing and is able to give in natural language in the chat of the Minecraft the advice that the humans. There are many different details and about the humans and how they behave, but the idea is that if you give explanation, then the hypothesis is that they're going to be much more willing to comply. And of course, also the other thing is there is also this relationship to trust, because if the expected outcomes come to pass, then the students more likely to trust the advice. And then they are also more likely, if they trust the advisor and the advice, they are much more likely to comply. And on the other hand, if the advisor gets something wrong, they are less likely. And I don't know whether you've done work on trust. We've also done a lot of work on trust, and we know that trust is dynamic. So even if they trust the advisor before, if he gives a wrong advice, then their trust may decrease. And so then it's difficult, once trust decreases, it's difficult to actually reinstate it. And so also, of course, the issue is not to overload humans with advice. We've done some experiments and we see that people don't really want a lot of advice, because especially in this critical and time stressed environment where they're running around trying to find the victims and save the victims, they don't want to be interrupted to have advice. So the issue then about compliance with advice, there are so many different issues about whether the human in particular is going to comply or not, that I think would be a very interesting part of the intelligent disability and rebel agents looking at these additional issues, especially with respect to humans. And so explanation in this talk is useful, first of all, in deciding when to obey or disobey, and also in increasing compliance as a kind of persuasion technique of increasing compliance with the advice. And here are the people that contributed to this work. So thank you very much. And I hope I'm not out of time or too small or too little time.
Definitely not out of time. Thank you, Katia. That was fun. I was waiting for you to get to the rebel agent disobedience stuff, and I think it really paid off when you did.
Yeah, thank you.
So the point is, and of course, as someone like yourself, and I also really enjoy the topic of explanations. And the point is that there's a huge role of explanations as to whether or not to in some sense, tamp down the potential disobedience of the agents that are receiving those explanations. And that's one of my takeaways from your presentation. By the way, when you talked about the example of GPS, I'm reminded of my own daily situation in which my system seems to be fixated on trying to give me the shortest possible route when I want the well, I want the route that gets me home as quickly as possible. So I struggle with that myself every day. So,
Well, I mean, the thing that is very interesting, if I may say so. So we were invited at a wedding outside of Pittsburgh, and we more or less, know the routes and all that. And so we started, going to the highway. We had the GPS, fortunately, and the GPS told us to go over a bridge into a tunnel. If anybody has been to Pittsburgh, they know that there are 5,000 bridges. I mean, really, and tunnels and so on. And this little, after you go over the bridge, this little thing that we had never really knew it even existed, was this little, we said, what is going on?
Right, there's no explanation.
I've never been in this, I've been here 30 years or whatever. I've never even been this way. But we said, okay. And there was no explanation, right? Okay, we'll just trust it. Okay.
Mm-hmm. Mm-hmm.
And we went, and then we could see from above that there was this total, traffic jam on the highway because there was construction. So we said, thank God we went to this. Then we arrived at the wedding. Everybody was late because they had been trying to go from the highway. And here it is, this was just a very, very totally extraordinary piece of advice, and we've never. So it is very much distrust.
Right. So, well, I should open it up first of all. Does anyone else have questions for Katia?
So to follow up on your example, I think that it really relates to something that we had discussions earlier. I think that, Ben, you were one of the people we talked about that. The fact that sometimes when we reason about rebellion and disobedience, we need to reason about the fact that interactions are longitudinal. We're gonna have to interact with the same agent again and again. So we need to trade off not just the immediate reward of disobeying or choosing whether to force or convey some intention, but also what will be the impact on trust in the long run.
Exactly. And I mean, this is very much the case, because first of all, trust is generated by repeated interaction, right? Unless there are a priori antecedents of trust, which means why do we have certificates, or why do we have certification of systems? You have a certificate and you say, okay, if the system is certified, I've never used it before, but this external authority has actually put a stamp of approval, and so I kind of trust it a priori, which is the case in our GPS, for example. We said, okay, let's trust it, but okay. But the other thing, as you said, Ruth, is longitudinal, and the thing that is very interesting is that the trust is dynamic. And so that's the thing, depending on the interaction with the system may make a mistake. And then people, what we have found, and actually in the literature have found, is much easier to mistrust, to lose the trust, than to actually re-establish the trust. And so this is one of the problems, the big issues that we have with our agent now in this other project, is that, and we haven't gotten the results yet, we're going to be running this experiments and so on, human experiments. But the issue is that our agent needs to give the advice to the humans. The humans are in a stress situation. They are in a team. And so you need to give also to look at team processes and advice to the team in terms of their strategy and things that they do as a team. And so recognizing a team strategy is impossible, right? You cannot computationally say this is a strategy. I mean, I can see what each of them do, right? But to say a strategy like they are synchronized, what are the features of these things? Mm-hmm. And how then the fact that they are synchronized or not lead me to give what kind of explanation or what kind of intervention, let alone what kind of explanation. And unfortunately, the thing that is very interesting is that there is a lot of work on human teamwork but the their results and so on are on the aggregate. So they are not like, I mean, they say, okay, we have this condition, so we take the average performance of people in this condition and this condition. And when they talked, whatever, they did better than when they didn't talk, for example. Now that doesn't help me at all if I have a team that I have to give an advice now, because that's an aggregate thing and so on. So it's like saying, well, people that smoke have such and such a thing of getting lung cancer. Well, now by seeing somebody, I can say, yeah, you have, I have a prior, but I don't know anything about that particular person. So it's really when to give the advice also is very important. So the thing that is interesting also in terms of these like disobedience and all that is it also time dependent and context dependent and norm dependent? So they are very interesting, especially if one is thinking about autonomy in military situations, and when to obey, when to disobey, what are exactly the norms, how are they, what's the context of the norms, how do you recognize when something fits a particular norm and so on. These are just totally open-ended, huge research.
So to close the loop, you started
Yes.
about talking about certificates for short term as a way to enforce that an agent can be trusted, and then you talked about different aspects that can change the trustworthiness of an agent, and in the long run how it can change due to temporal changes or contextual changes. Would you say that you can bridge this gap by having certificates for an agent, like when you
Yes.
I think of my work with the Singai robot, having a robot with a vest of a service dog, like a service dog, should convey, and this is a research that is ongoing, we're doing it now, but we are interested in seeing whether it's a sort of a certificate, like this robot knows what it's doing, like this dog knows that it's a service dog, it's not just a regular dog wandering around.
In context of norms that are expected under that circumstance, right?
Yeah.
Exactly.
Yeah. So in the trust literature, and we go a little bit towards trust rather than in the trust literature, this is called fiduciary trust. So there is many different types. Fiduciary trust means that you have a particular role. So you are, a physician, right? I go to the hospital, and the hospital has, a physician that is a cardiologist, whatever it is. I don't know the person from Adam, right? I haven't, known, I haven't even gotten his CV, and I don't go there and say, please show me your medical certificate or whatever. So this is fiduciary trust. For a lawyer or a teacher, I go to university, I see Ruth right there in the classroom, I have to trust that she would, did this. So this is really fiduciary trust that people have. It's the same, why I'm saying that, because it's the dog having a particular thing that says, okay, guard dog, that gives it the fiduciary trust for somebody, for example, that would take it, that even somebody, not the handler, but somebody else, for example, right, would recognize it as such. And there are other different types of trust. Now, on the other hand, what is very interesting is that people could overtrust. And so one of the important things, now we go from disobedience and so on, but I think trust is a very important thing in obeying or disobeying. That's why we have this discussion, right? And the issue is that, again, the most important thing is the so-called trust calibration. Trust calibration means that I trust the entity that I should trust, and I should distrust the entity that I should distrust. Because if I'm not properly calibrated, I may overtrust an untrustworthy agent. And that is problematic. I mean, it's not even malevolent. I'm not talking about deception or anything like that. I'm talking about something that is, you know, a little bit faulty or something, you know, has lost, you know, some valve or whatever it is, you know, that it is lost. And
you talked about teaching, for example.
So well, yeah, for example, suboptimal, you know, teaching, the person doesn't know, and it's not anything malevolent or anything like that. Now, the point is that a lot of people may, as we've seen in the literature, with anthropomorphism, but there are many, many aspects. But one interesting thing, because we were talking about certification and the dog having this thing, is Alan Wagner's a very interesting experiment that he did, where he had this this robot with 2 antennas, right, and was there in a fire, and the robot was pointing to people. So there were people there, a few students, right? I mean, this was the experiment. A few students go there in the corridor, you know, they talk, they're going to a conference room, whatever they were supposed to. All of a sudden, you know, there's a fire, there is smoke, there is the fire alarm, whatever, you know, starts going. And so then there is this robot that had, you know, was there when they went, and it had these things that were showing. And so a robot starts pointing particular ways. And the students, although there were exit signs that they could see in the building, there were exit signs, they were following the robot because they assumed that it was a guard. It had this, okay? So this fiduciary trust that was assumed. And so the robot managed, I mean, it's just very interesting, to even take them to like rooms without windows or whatever. I mean, just the worst place to be in a fire, right, is to be in a room where now there is no window, no door, except to go there, right? And they just sat there. I mean, and so anyway, so it's very interesting because that shows that, and you can find, you know, the paper, but that shows that really, if you overtrust, I mean, if you don't kind of think about it, even about authority or about this fiduciary trust, you may really get yourself, you know, into really stupid situations. So that was, it's one of these fun things that is counterintuitive, and was actually, student driver sticker. So for example, so that's exactly right, and there are all these different contexts, and how people, you know, trust, and of course the other thing is the cognitive workload and so on. So if you are cognitively stressed out, even if you have an agent that you have seen that it makes mistakes, then you are going to use it, because the issue is not only trust, but also trust and delegation, right? So if I have an agent, not only is whether I trust their advice, but am I going to trust them with some piece of work? For example, my secretary, I tell her to do my travel agent, whatever, you know, my travel. And so that is the really, you know, do I rely on this agent? I mean, this is the proof, right? I cannot say, okay, I can just say I trust you, whatever, in experiments. But where the rubber meets the road is, do I really give this person or this agent, you know, some piece of work to do on my behalf? That, you know, then I really,
Very interesting contribution, Katia, because it's different from what I was anticipating, I guess, because we earlier had a presentation that pertained to situations in which a teacher may want to deceive the student and in some sense not give them the optimal advice. And you also were making me think, well, maybe you're going to get to the point in which the student is purposely disobeying for some reason I couldn't anticipate or something like that. But instead, the theme that I'm getting for the entire workshop, in which yours is definitely a focus point, is that you really have to interpret what the behaviors are to understand whether or not, as in your example of the GPS, route finding example. Is this being deceptive? And your point of the relationship to trust, and that's really interesting.
Yeah, yeah. Yeah, and even when it's not deceptive, there are all kinds of really very interesting and bizarre, I mean, things that one does not like following, you know, this faulty robot and so on, getting yourself into, without any intention to deceive or anything like that, you know, just, and so from that point of view, the issue is now, of course, we have our psychologist friends that need to study the humans, because the humans are the ones that have really a lot of, shall we say, you know, idiosyncratic things and bizarre, I mean, non-rational, right?
Yeah.
Ways of thinking and behaving. And that is what breaks an agent, for example, that would give advice or whatever. The human says, what are you telling me? I'm not going to do that.
Yeah. Are there any other questions for Katia?
Yeah, I think really fascinating talk. It's sort of very stimulating. The line of thought that it stimulated for me was just wondering about the norms about taking advice, because, you know, I think a lot of the work here sort of in terms of disobedience and rebellion sort of assumes a sort of superior subordinate role. And if you're a subordinate and you disobey a command given by a superior, then it's pretty much understood that, you know, all the time in that one specific instance, you really need to have a good justification for that. But the norms, to me, regarding advice and taking advice seem to be that they're just built in, that there's might be a little wiggle room there, right? You know, you don't always have to take the advice given to you. That's why it's advice and not a command or an order or something like that. And it's very context dependent too, depending on, you know, if it's a student teacher versus just giving advice to your friend or something of that sort. So I don't know, just wanted to hear your thoughts about, you know, how that kind of connects to the theme of rebellion to you. To what extent, how much do you actually have to ignore taking advice before you're sort of, you know, being a disobedient agent or a rebel or something?
Yeah, I mean, so it depends, right? Because you know, being a rebel is a social construct, I would say. There is no, you know, rationality or objectivity. So in different societies, obviously, different behavior would be considered rebellious behavior. And so that is, so context and norms in a particular society is very important for that. Now, that being said, then again, it is also the interesting, so in the normative, so if you look at the, you know, the deontic logics and so on, that basically formalize norms. There is this issue or this construct, this formal of sanctions also. And so one does a calculation, in some sense, the agent, in terms of breaking a norm, which would be this rebellious behavior, right? Or, you know, and what would be the sanctions for that. And then, of course, what you have also is that you have, in terms of norms, you have a taxonomy of norms in some sense, right? Conventions are norms. So if I sit at the table, most people would take to eat meat, they would take, for example, on their right hand, the knife, and the left hand, the fork. Now, if I don't do that, it's okay. I mean, the hostess is not going to not invite me again, you know, depends. But you know, all the way, you know, to moral, of course, imperatives and all that kind of thing. And so the thing is that in terms, you know, breaking these things, it is also very much, and this is another problem when we are trying to talk about ethical decision making of robots and things like that, because these are very much context dependent. Very, very context dependent. And I'll give you an example. We've looked at some of that, and we had a model and also did experiments with people of different cultures as well. So an example is very, so suppose you have an agent that you have told, you are the owner of the agent, right? And you say, if there is, you know, a phone call and I'm at table or something like that, please come and tell me what the message was. Okay. That's all well and good. You know, you are with your family, the robot comes in, says, okay, you have this message from somebody, somebody. Now suppose that you are looking for a job and your boss, you have your boss for dinner. And now that robot comes, and we're talking about privacy norm, for example. And so now the robot comes and says, well, you know, your interview with this other company, you have a message that your interview with this other company for this job is tomorrow. Okay? So what is the context now? The context is just one other person. If it was not your boss, it wouldn't make any difference. So what I'm trying to say, how is one going to model and create a thing where you know, this very small, very small part of who is sitting at the table next to you is so important. Let alone, you know, you're with your wife and your girlfriend, I mean, all kinds of things, right? And so now this robot needs to have, you know, a social, I mean, not only the norms, but the privacy norm and all these kinds of things, but again, in this particular case, who would be? So there needs to be a lot of background knowledge. What does it mean to have a boss? What does it mean to whatever, and so on and so forth. And so this is, and you can imagine, you know, I mean, in other kinds of situations. What it would be. So it is very interesting and totally open-ended how one can really model these things. And what would the robot now be thinking? So a robot, loyalty norm. A robot sees you taking your hostess, you know, silverware. What should the robot do? Behaving ethically. So the robot has a dilemma now. Tell the hostess that Katia is taking, you know, your silverware and put it in her pocketbook. Not say that, which of course, if the robot has been programmed to be, you know, a lawful citizen and so on, but also it has been programmed to be a loyal to you. What would the poor thing do? And then if it, I mean, one can get more bizarre, you know, now the robot gets to testify against you in court and so on and so forth. What is the reason? Anyway, there are all these things that are very interesting in these things. And they are just, as you can imagine, you know, computationally tractable, even to model them, kind of intractable. So we can do baby steps, right? And hope for the best.
Any final question for Katia? If not, we should.
I will just add, because I think it's very interesting, because we started with Dylan talking about value alignment, and now we finished with Katia. And Katia, you talked about, so I think that one thing that maybe a default approach that a lot of researchers take to this dilemma that you raised is, if you're unsure, don't do anything. Like if there is a safety issue or something that the context might change, so it might affect your decision somehow, don't do anything that's like, try to minimize the risk in a sense. But I think,
yeah, but the point is that then you're not, you know, now our robot that is very good citizen and so on cannot be true to himself, to its.
That's absolutely.
And also, you know, now talking about that, that's more, you know, whatever, but not doing anything is not, so that's the point, it's not really the answer. I mean, it's a cop out on the part of the research community, right?
Absolutely. Yeah.
I
And
mean,
I think that
for computational reasons, I understand that. I'm talking about, the actual, high fidelity, for example, modeling of the thing, right?
so that's exactly what Dylan was talking about in the first talk of the day, that the more features or the more objectives you incorporate, the better accuracy or alignment you might get.
Yeah.
Assuming those
So
features are relevant.
as long as these features are relevant. Yeah, that's a good point.
Exactly.
So
Exactly.
this begs the issue of uncertainty. The point is that if we could get away from the cop-out that you're mentioning, Katia, if we just take actions in order to be able to gather further information. So, and to get to be more certain as to whether or not the context is appropriate for the advice giver. Right? Go on.
Yeah. Yeah, I mean, modeling context is one of the most, slippery slopes, right?
Yeah.
And I remember, well, in the vision community, for example, they've looked at that and they have a little bit more, because now there is, what is the context, what is the object and what's the background?
Right. Okay, well, thank you very much, Katia. It was a wonderful talk. Greatly appreciate your contribution to the workshop. And it's certainly got us thinking.
Yeah.
So,
Thank you.
okay.